Frictional Forces by Zoe, Sydney, and Olivia. Hypothesized that if the surface area has a greater frictional coefficient, then the change of energy of the box will be greater due to work of the frictional forces on the objects. We hypothesized that the blanket will have the greatest frictional coefficient, next velvet, and then the wood. We have independent variables of frictional coefficient of the surface. Dependent variable is the amount of energy lost in the box. Work done on an object can be described as the change of EK. In order for the block to gain or lose energy, there must be work done on the block. If no energy was lost, then the objects have a potential energy at the top of the ramp should be equal to the kinetic energy at the bottom of the ramp. Therefore, we can conclude that the block's kinetic energy does not match the potential energy, and there was work done on the system. In this observational study, we are looking at the different surfaces with different frictional forces affect the amount of work done on the block.
On this slide, there are two photos. The one on the left, you can get a good look at our setup with the cardboard and the table making our ramp. The photo on the right shows the ramp covered with a blanket. You can see how we changed the material but kept the ramp constant. Our methods were as follows. The ramp was made of cardboard and was placed against a table to make the angle. Tape was placed on the cardboard to ensure stability of the ramp. The frictional block was slid down along the tape and kept constant. Videos were recorded and analyzed using the tracker software. During every trial, it was made sure that the block ended at the bottom of the ramp. When tracked, it was made sure that the video stopped at the same spot in order to keep our calculations for velocity constant.
The data we found using tracker was the wood block had a final velocity of 1.58 meters per second before hitting the ground. The velvet box had 0.939 meters per second, and the blanket surface had 0.764 meters per second as its final velocity. In order to calculate the work done on the box, we first found potential energy using the mass times the force of gravity times the height. We then found the kinetic energy using our final velocities that we found using tracker, doing 1/2 the mass times the final velocity squared. All three boxes began with the same potential energy, however, the kinetic energy varied for each box. The largest kinetic energy was the wooden box on the ramp. In order to calculate work, we minus the kinetic energy from the potential energy. This gave us the work done by the frictional forces. The blanket under the box had the most work done on the box, while the wood-covered box had the least amount of work done on the box. In order to calculate our friction coefficients, we determined that the force of friction was equal to the work done on the objects. Therefore, we could find the friction coefficient by dividing the force of friction by the normal force. The normal force was the mass of gravity times the sine of the angle of the ramp, which was 44 degrees. The wooden box had the smallest friction coefficient, while the blanket under the box had the largest friction coefficient.
The force of friction is equal to the work done on an object. The frictional coefficients are equal to the force or friction against the normal force. The velvet box friction coefficient was negative 0.5747. The wood box was negative 0.566, and the blanket was just negative 0.5965, which concludes that our hypothesis was correct. The blanket had the highest frictional coefficient, while the wood box had the smallest frictional coefficient. This concludes that there is more work done or energy used in order to push the block down a blanket surface rather than a just plain wood surface.